hear other people's counter.
Like a very long time. Still adjusting to like the
They have plenty of
so very different.
I had an uncle who was
Are you on a
yes, we can supply you with stuff. I mean, this went from, at this meeting, this went from universal disbelief to tittering acceptance to, gee, if that's really going to happen, this would be great. So, 5,000.
Well, the trouble with turning off the lights is you think you're supposed to start.
But the other thing is trying to get 4-star to not disappear because it's occupying a baseball court. And it's not used a lot, but they work with the data reduction software. Almost damn near impossible. But we can, it was written for a Mac circa 2010. Yeah, well, I got it a week and a half ago, and I got it to work out. It was open, and it involved WCS twins.
yeah, but a lot of them
Getting them properly.
yeah.
It is possible. It hasn't been possible because we don't care what service laboratory and service from
No, first time. Okay. Okay, sounds good, yeah.
So yeah, yeah,
Yeah.
yeah, well, still, I feel like I shouldn't be spending my time supporting something. I do.
Oh, you're right. But now we're just resubmitting revisions.
Yeah, all the instruments, the data reductions.
All instruments like major.
Okay, welcome everyone. We have just finished an interesting discussion on intermediate mass black holes without definite conclusions. So both LISA and X-ray telescopes are welcome, right, Igor?
Yeah.
And that's the best approach because we don't want to dictate to observers which instruments to use because they might surprise us. So, and we have 4 presentations today at the lunch. The first would be Dipto Mukherjee, who's visiting us, and he's finishing his PhD at the Carnegie Mellon. And he will talk about exploring the capture and retention of interstellar objects in near-Earth orbit. After that, we'll hear from Rachel Patton from Ohio State. Where is Rachel? Here she is. And she will tell us about binary interaction and the explodability of massive stars, which is a very interesting term, explodability. Difficult to say. And then we'll hear from Furkan Ozturk here at Harvard about the origin of biological homochirality by crystallization of an RNA precursor on a magnetic surface. This is a very interesting piece of work, and one of the biggest puzzles in the context of life is why is there one chirality preferred, and we will hear perhaps a possible origin for that. And finally, Daichi Hiramatsu, here from the CFA, will tell us about from discovery to the first month of Supernova 2023 IXF in M101. Dipto, please.
Am I audible? Okay. So, hello everyone. Thanks for the introduction, Avi. My name is Dipto Mukherjee, and I'm visiting here from the McWilliams Center for Cosmology. But the thing that I'll be talking about is not cosmology. So this is a piece of work that we did recently looking at the capture and retention of interstellar objects in near-Earth orbit. So as we know, interstellar objects are all the hype right now, and they carry with them a wealth of information about processes ranging from like stellar formation to stellar chemical composition to planetary dynamics of extrasolar systems. And people have sort of wondered if we can, like detect these objects in our nearby to, study them and understand the wealth of information that they carry with us. So people have sort of explored this idea that, as an interstellar object is in a hyperbolic trajectory around the sun, because of the interactions with different planets, they can get captured into our solar system. And as you can see from this animation, what happens is like it, encounters with the orbit of, let's say, Jupiter, and then gets captured into a bound orbit around the solar system. Now, most of the work in this regard has been looking at, captures into distant orbits, like long period comets or like Oort cloud-like orbits. But what about something like closer to us, maybe something in near-Earth orbit? If such a population of these interstellar objects, these captured interstellar objects exist, and they're different, they're different from like a background population, it would possibly be easier to visit by space probes and detect, and that could help us expand our knowledge of these interstellar objects. So our work was motivated to understand if a possible population of captured interstellar objects exists in near-Earth orbit. So in order to do so, what we did is we did a bunch of scattering simulations. And so the first scattering simulations were done with the Earth moon because we were trying to capture into near-Earth orbit. So we tried to understand if Earth can contribute any fraction of these captured interstellar objects. And the obvious candidate is Jupiter because of its mass. We varied the incoming hyperbolic excess velocity, this V infinity parameter, and we varied, for a fixed V infinity parameter, we varied this impact parameter B to calculate this cross section, where this B max is the maximum impact parameter sampled. And to calculate this N captured, I'll mention, we had to look at objects that were captured into very specific orbits, these near-Earth object orbits. So the first thing that we need to understand is what sort of encounters can lead to capture in these closed bound orbits or near-Earth orbits. So here I have presented a 2D histogram of the captured semi-major axis, the bound semi-major axis, versus the minimum distance an object encounters with the Earth-Moon system. And you can see that if you want to capture anything below like 500 astronomical units, you need an encounter that goes within the Hill radius of Earth. And that happens to be true for Jupiter as well. For Jupiter, the limit is actually less than 50 astronomical units. So that indicates to us that if you want to capture objects that lie within, let's say, the orbit of Neptune, you need close encounters. So in order to calculate this sigma, the cross-section, we actually need to calculate the cross-section of close encounters, which I call sigma sub c. So if I want to calculate the sigma sub c, what I do is I go and select these objects with a very specific semi-major axis, semi-major axis of A less than this threshold semi-major axis, which I call A sub t. So here I've presented the cross-section of captures occurring with a semi-major axis of less than 10 astronomical units. So the final captured object lies at a semi-major axis of less than 10 AU, which is the semi-major axis of about Saturn, and lies in near-Earth orbits, which I define to have a perihelion of less than 1.3 astronomical units. And at the outset, you can see that the captures are completely dominated by Jupiter, which is about 10,000 times as efficient as the Earth-Moon, which is not very surprising. Jupiter is like the most massive planet in our solar system, so it's not surprising that it dominates the capture cross-section. And you can calculate this capture cross-section as, by differing this, instead of 10 astronomical units, you can, put an upper limit of 20, 50, 100, whatever you want. So the next thing we explored is what do the orbits of these captured objects look like? So here in black and purple, I have presented the known orbital parameters of the known near-Earth objects, and that from a d-biased population that was obtained from Granvik et al. And at the outset, you can see that the captured population looks very different from the so-called detected population of near-Earth objects. In particular, the most jarring difference is in the distribution of eccentricity. So here what I've presented is 1 minus the eccentricity. So if it's like close to, like 1, that means it's mostly circular. But what you see from this plot is that most of the things that we capture are very centric, sometimes have eccentricities of somewhere between 0.95 to 0.99. And they're mostly captured in prograde orbits, with about 10%-ish being captured in retrograde orbits. Now, that fraction is larger than the known retrograde population, and it's also like more eccentric than the known population. The average semi-major axis of these captured objects is also like much larger than the known semi-major axis. So once we have the cross-section, what we can do is we can calculate this velocity average cross-section to see what the velocity average cross-section looks like today. So we have this functional parameter of incoming hyperbolic excess velocities, which we assume to be similar to the field star velocity dispersion. And once we have calculated that, in order to estimate a population, we need to understand how long these things survive in near-Earth orbit. So what we do is we take our captured population and put them in a solar system containing all of the planets, and we see how long they survive before they're getting ejected or merge with a planet or collide with the sun. And we find that they lie in highly chaotic orbits, which is not surprising. And the average lifetime is only about 0.5 to 1 million years, which is lower than the bulk lifetime of known near-Earth objects, but it's comparable to near-Earth objects arising from the outer asteroid belt. Now, we have almost all parts of the puzzle to estimate a population of these objects in the present day. So in order to calculate the number as a function of, let's say, the size of the object, which I call d, which stands for the diameter, what I can do is I can take the velocity average cross-section, multiplied by the number density of these objects for a particular diameter d, and multiplied by the lifetime, which I take to be the average lifetime. To estimate this number density of interstellar objects for a particular diameter d, what we do is a very simple scaling relation based on the number density of Oumuamua-sized objects, which is calculated to be about 0.1 per AU cubed, and this diameter of Oumuamua, and scale it using this scaling parameter 1 minus q, which depends on sort of like the ejection process. So q lies somewhere between 4 to 4.5, which puts limits on the population statistics. And so very clearly you can see that the population is completely dominated by objects that are about 1% the size of Oumuamua, so have a diameter of 1 to 2 meters. And then you have these 10 to 20 meter sized objects, which there are about 1,000 of them within within the orbit of Saturn that are present in a steady state population as well. Interestingly, we also find that if you have something about half the size of Oumuamua, you have about an order of 10 of those lying within the orbit of Saturn and in near Earth orbit. But unfortunately, we don't find anything within that is the size of Oumuamua. So these upper two ones are harder to detect because of their small size. But if you assume that this captured object has the same albedo as that of Oumuamua, you can we predict that we should be able to detect at least one such captured object by LSST. I'll skip this real quick, but essentially what it shows is that most of the objects that survive lie in retrograde orbits than prograde orbits, so highly eccentric retrograde orbits might be a good target to see if these things lie. So in conclusion, the simulation suggests that a steady state population of these captured ISOs exist, and it's highly likely for 1 to 20 meter sized objects to be present. And since retrograde objects survive longer, maybe highly eccentric retrograde centaurs could be a good target. And just before I end, I wanted to give a very brief slide about me. So I'm a fifth-year PhD candidate at Carnegie Mellon. I do gravitational dynamics at all scales. Actually, most of my previous work has been related to looking at LISA sources, so massive black holes in nuclear star clusters. And we have a current paper coming out in about 2 to 3 weeks, so keep an eye out for that, about looking at gravitational wave imprints of dark matter. And I'm also looking at galactic modeling of interstellar objects. So I'll be here until tomorrow, so if you want to chat, please feel free. I'm happy to chat about anything. Thank you.
So Dipto, as you know, there is a catalog of near-Earth objects from pan-stars, and we're hoping that the LSST will increase the number. Is there any candidate object in the solar system that we know about that could be interstellar?
So I believe Namuni and Morias. I am sorry if I mispronounced their name, but they have they had a candidate list of these retrograde centaurs that they believe could have origins from interstellar space that were captured in in the last few million years. We don't have any candidates for captured near Earth objects yet, because as you saw, the objects that are supposed to form a steady-state population are kind of weird, like on these highly eccentric retrograde orbits. But hopeful for LSST to discover some of these things.
Right, and how would you, you can't, unless you land on it, you won't be able to tell the composition, right? Or from the reflection of sunlight, can you tell if they're interstellar?
Probably not. So at least dynamically, what we are expecting is, like, if you, like, at least dynamically, if the population of interstellar objects that surrounds the solar system is anisotropic in some way, like if it has like a preferred, like, you know, velocity dispersion or like inclination or something, maybe we can identify a population that has inclinations that are different from what you can produce from a background population, like maybe the outer Oort cloud or inner Oort cloud, because we have known hyperbolic comets exist. And but the Oort cloud is sort of like isotropic, it's spherical, but if there's some anisotropy in the interstellar object population, that will be reflected in the captured population.
Go ahead, Tony.
Well, different families of asteroids have different colors on average. And it's not that easy to determine the color of an asteroid because they're constantly tumbling and so forth. And an instrument, self-servingly, which I might point out, can do this is my instrument, Pisco, because it does all of the colors at once. And so you open the shutter once, you get all four colors, and close the shutter.
And you expect the color of an interstellar object to be different because it's exposed to cosmic rays differently?
And it might have a different composition. I mean, you know, I would say looking for anomalous colors would be one way to tell from a distance whether the object is likely to be interesting or not.
And of course we can land on it at some point. Go ahead, Juliana.
Question for you, or maybe you. So let's say we could land on this object. You said that the lifetime was on the order of 1 million years.
Yeah.
What sort of processing would you expect on the surface of this interstellar object from dust or other effects in the solar system that might start to masquerade the object as a resident?
So I can't really speak to the chemical composition of these things. People have sort of hypothesized that they have like, different isotope percentages compared to objects that arise out of the solar system.
So you're really looking for a unique properties of the orbit.
Yeah, I'm mostly focused on the dynamics portion. So like, if we find a population that lies on these weird retrograde orbits that, you know, are somehow hard to explain with like the background population, maybe like ejection from the Oort cloud or something, that could provide a hint that, you know, maybe it originated from interstellar space.
And of course the composition will depend on the source. There are so many possible.
Yeah.
I mean, the most common would be M dwarfs.
Yeah.
Okay, well, let's thank Dipto.
The screen seems to have turned. Aha! How odd. All right. Hi, everyone. Thank you so much for the opportunity to talk briefly about what I've devoted a large portion to my PhD studying, namely how binary interaction affects the explodability of massive stars. So massive stars die in spectacular fashion, either exploding as a supernova or collapsing into a black hole. And the very simplified explosion landscape that we get presented early on is this, that stars below 8 solar masses will not explode. Stars between about 8 and 25, 30 solar masses will explode as a supernova. And above 25, 30 solar masses, these stars will implode and form a black hole. An extensive body of research, especially over the last decade in 1D neutrino-driven supernova modeling, has shown that the explosion landscape is far more complicated, where instead of these continuous regions, you get explosions and implosions interspersed with one another. So this term explodability that I used really comes from what people have coined these islands of explodability, or regions at higher masses where you would normally expect an implosion, but you get an explosion. And the key insights from these models is that whether or not a star explodes depends sensitively on the structure of the core immediately preceding core collapse, which is an excellent insight. But the problem with these models is that these are all from single star progenitors. But massive stars are hardly single. Massive stars live in binaries, if not higher order systems, as we see in this plot on the left, which is the multiplicity fraction as a function of initial mass. And when stars live in binaries, they can experience very complicated evolutionary histories. They can enter a common envelope phase, they can have their envelope stripped, they can merge with a companion. And all of these things will change the internal structure of the star, which carries over into core collapse and can affect the explosion landscape, the explodability of these stars. So what we want to do is to create an explosion landscape for binary interaction, but this is very difficult because you have binaries existing over a wide range of initial conditions. So ideally, we want two things. We want models that are agnostic of evolutionary history, that give us the structure of stars at core collapse, regardless of what sort of complicated interactions they've had. And also, for ease's sake, we want these models to be as simple as possible without losing accuracy. We can do this by exploiting two main properties of the late-stage evolution of massive stars, namely that once a massive star reaches carbon ignition, so carbon ignition and beyond, the carbon-oxygen or CO core is changing so rapidly that the envelope and the helium shell can't thermally adjust in time. So late-stage evolution is essentially core evolution. And core evolution is set primarily by two key properties of the CO core at carbon ignition: its mass and its composition. So if we know those two things, we can generate a grid of cores where we manually set the initial conditions of the star and continue their evolution to core collapse and see the structure regardless of what happened to the star prior to carbon ignition, because those sorts of interactions would just change these two starting conditions. And that's what we do. That's what I've done using a grid of about 4,000 models in Kepler, a 1D evolutionary code, and also verified these results in MESA. We took bare, non-rotating CO cores where we manually set their composition through carbon mass fraction and mass, and we evolved them from carbon ignition to core collapse, where at core collapse we probed their structures. And this is what we find. We'll see lots of these plots. This is carbon mass fraction versus CO core mass that we set at carbon ignition. And the distribution is the structure at core collapse. This distribution happens to be for the compactness parameter, which is essentially a radial gradient in mass at a fixed point within the star. And we see a lot of details here. First, I want to point out that you have two dominant regions, these higher values of compactness, which tend to correspond to implosions, and these lower values of compactness, which tend to correspond to explosions. And this tracks well with what's physically happening in the core. The amount of carbon you have in your core will determine whether you burn carbon convectively or radiatively, and that has ramifications for the subsequent evolution, which is why this transition to dominated by implosions tracks well with how you're burning carbon. And lastly, I want to point out what are coined these islands of explodability, where even though these cores are in regions where you would expect lots of implosions, you can actually have combinations of core mass and carbon mass fraction that give you stars that are easier to explode than more difficult. And now our grid covered a larger range of initial conditions of cores than are attained by actual stellar populations. So to show you where actual stellar populations fall, let's first look at the plot on the left. This is the same plot as before, but now I've overplotted the single star models from Sukbot et al. 2018 in black and the binary helium star models from Stan Woosley in red. And we see that these populations, like all stellar populations in this domain, fall in very well-defined regions. But these helium stars, which are strip stars, despite having the same shape as the single stars, lie in a different plane. So experiencing an interaction has moved them coherently in this plane. And the reason why is shown on the right. This is a set of BPAS models from my 2022 paper, where we have both single and stripped stars. And the color coding is the amount of the envelope that the star has retained. So single stars, or stars in wide binaries who will not have their envelope stripped or stripped entirely, fall on this lower sequence that corresponds roughly to the black stars on the left, where these stars have retained their envelope. But stars that are stripped have an increased carbon mass fraction because when their envelopes are stripped off, their helium core recedes, and that changes the density, it changes the amount of helium that you can bring in, and ultimately affects the relative nuclear reaction rates that would give you or take away carbon. A lot of work has been done studying stripped envelope supernovae and the effects of envelope stripping on massive stars. But there's very little work on the long-term evolution and structure of merger products, which is what I want to spend my last couple of minutes talking about. So at least 25% of massive stars should merge with a companion, and depending on the evolutionary states of when they merge, you can get very different outcomes. Stars which merge on the main sequence will behave as single stars of the new combined mass. But when you take an evolved star and merge it with a companion, you're creating a star that will not behave like a single star because you have a developed helium core. So as a very simple initial test case, I took an 11 and a 4.4 solar mass star on an 11-day orbit, and I evolved them to the point of contact in MESA. MESA can't handle common envelope evolution or merging, so we had to make an approximation for what the merger product would look like. So you can do this in a couple of ways. I don't have time to go into the details, but you can either rapidly accrete the secondary onto the surface, or you can splice up the stars by their entropy and sort them. And in this latter case, you end up with part of the secondary penetrating deeper into the star, and that does have ramifications for the structure. But what we see now in this carbon mass fraction versus CO core mass plane, again, now comparing to MESA models of stars from Fabian Schneider, is that these merger products, this red point and this pink points, lie in a very different region of this plane that is unattainable by other types of interaction. And if we think back to the distribution of final structures that I showed, things that fall below this single sequence tend to be more difficult to implode. So despite these cores having lower mass, despite these case B mergers being or having lower mass helium cores, which are easier to explode, their composition changes actually could make them more difficult to explode. And yes, I won't go into it in detail, but there are some differences between these two different ways to form a merger product, but both types of merger products, rapid accretion and entropy sorting, show this behavior, at least in this model. So moving forward, there are several things that I would like to do to explore this in more detail. One is generate a grid of merger products in MESA and continue their evolution to carbon ignition and, where possible, even core collapse, to look at these structural changes and compare to single star evolution and compare the differences between entropy sorting and rapid accretion. I also want to look at structural differences of merger products that produce the same equivalent mass but come from different initial conditions. You know, does an 11 plus a 4 produce a star that's very different from a 14.5 plus a 0.5? And then lastly, for the merger products which do explode, what are their nucleosynthetic yields and how do those compare to single stars as well? So I'm just about out of time, but in short, the structure of a massive star is very important for determining whether it will explode as a supernova, and different types of binary interaction will coherently change the internal structures of stars in different ways. And lastly, I am very excited about the prospects of exploring the effects of merging on the explodability of stars. Thanks for your time and attention.
it looks like there is an elephant in the room, at least for me, but you didn't mention it, and I wonder why. Maybe you can have a good argument about it. Obviously, when you have a binary, there is accretion and angular momentum being transferred, and the angular momentum can prevent you from collapse because it's just, it may trigger explosion because you can't contract the core. So can you say something about the angular momentum, the rotation?
Yeah, so I didn't say it in the talk, but I purposefully neglected both the initial rotation of the stars and any spin up to the stars caused by merging, mostly for ease's sake. It's very difficult to do this in MESA. So my model was purely meant to be a proof of concept and an initial test case. But what I would like to do in the long term is, yes, explore, include rotation, both initial rotation and then spin up from merging, and to see how that changes structure as well. Because rotation will also change your nuclear reaction rates, and you get a different core structure from that as well from mixing.
I was going to ask about rotation. So
Okay.
the words out of my mouth.
Please go ahead. Yeah.
No.
It's okay. You can.
Yeah.
This is cool, but I'm wondering about these islands of explodability in your 2D diagram. And, is there an easy physical explanation for that? And the other question is, how does it depend on the detailed numerical parameters? The background of my question is if I speak with Alex Rieger or Georges Mény and so on, people who build these codes for a living, they tell me that the result depends super sensitively on the numerical parameters of why producing mixing links for this and that, how they are transparent atmosphere.
Yeah, so I would not say that the locations of these islands are absolute. I mainly wanted to highlight that we do see this behavior even in our simplified core models that people who are doing evolution of full stars are seeing as well. But you're right that the number of the islands of explodability and their location in this plane does depend sensitively on your modeling choices. But we do see, I have a few extra slides. So we did these models in Kepler and in MESA, and we did a smaller grid in MESA, and I downsampled the Kepler models. We made no attempt to make the MESA models look like the Kepler models, but we can still see the same sort of behavior even if the location of these islands are different between the two codes. So mainly, I think they're real, but you're right. The quantity and their location depends very sensitively on your modeling choices. I think I forgot the first part of your question.
Oh, the first question was, is there an easy physical explanation for these items, right? Because naively I would think there's a smooth transition and the physics does not change that much if I just increase the stellar mass by a tiny bit.
Off the top of my head, I'm not sure. I think if we looked at the Kippenhahn diagrams of these models, we might see movements of shells within the star that may change the structure, but I don't know.
Morgan, did you have a question?
It's okay, we can.
Any other questions? If not, let's thank
All right.
again.
What do I do with this?
Split
it through?
Yeah.
And then keep this in pocket maybe? All right. Can everyone hear me well? Is this working?
Yeah.
Okay, perfect. So my name is Furkan, and I'm a grad student in the physics department at Harvard, working with Dimitar, who is sitting here. And today I will talk about the chirality problem as it pertains to origin of life. And you may have heard this problem by being, astronomers. in relation to circularly polarized light, high magnetic fields from like neutron stars or cosmic rays. But today I will offer a different story. So let's get ourselves oriented. So we are talking about a pond on the surface of the early Earth about 4 billion years ago, just like the Gale crater on Mars. And to give a little bit of a big picture of like the origin of life and different stages, we first deal with the geochemistry and the feedstocks, meaning water, minerals, the gases in the atmosphere, the energies that are coming from, let's say, UV light, and in general, non-equilibrium. And these kind of conditions first create the monomers, and then these monomers kind of polymerize and create functional polymers like RNA and proteins, and they show some function like replication and catalysis. And then these polymers go into a cell, which we call the protocell, the earliest versions of the cells, which evolves to become the last universal common ancestor. So this is kind of the big picture. And we are dealing with kind of the left and most of this illustration where we make the first biologically relevant molecules like amino acids and sugars. However, we have a problem, which is called the chirality, homochirality problem. So chirality is a geometrical property, and objects that cannot be superimposed on their mirror image are said to be chiral, just like our hands, right? Right hand is not overlapping with our left hand. And most biologically relevant molecules are chiral. Amino acids, sugars, nucleic acids are all chiral. And they exist in symmetrical pairs, left-handed and right-handed versions. But the problem is biology is very picky when it comes to chirality. It selectively uses left-handed amino acids and right-handed sugars. And that is what we call homochirality, the homogeneous presence of chirality in life. And like, what is this, defining feature of life on Earth? Because this is ubiquitous. It's everywhere. So why does it really matter? Why does homochirality matter? Well, there are multiple reasons, but I will show two. So first of all, like when we talk about origin of life, we're talking about a network chemistry, like a lot of chemical reactions that are happening at the same time. An example is shown on the left. And in such a network, the yields of each step is very important, because when you have multiple steps, and if each step is throwing out half of your yields to the opposite chirality, then after several steps you just lose your material. And also, if you try to polymerize racemic nucleotides to make homochiral RNA, it turns out that it doesn't work out. And this has experimentally been shown that the presence of other chirality prevents the polymerization of RNA. So essentially, without figuring out chirality as early as possible, we cannot realize the RNA world. So let's break the problem into several steps. First, we start in a racemic state where each molecule is in 50-50 presence. Then, if we can somehow find an agent that couples the chirality, molecular chirality, and introduces a little bias to make one molecule a little bit more than the other. So let's say 1% more L than D. And after you amplify this to reach homochirality at that molecule, and then spread that to the entire network. So this is the homochirality problem broken into parts. So what is our approach? Well, we introduce an effect named chiral-induced spin selectivity effect that was recently discovered to break the chiral symmetry. So because of time constraints, I won't describe the effect and the experiments in a lot of detail, but I will give you the most important bit. So cis effect is about how electron spin couples to molecular chirality. And what cis effect says is, if you transport electrons in a chiral potential, the electron motion in or through the chiral potential is spin selective. So essentially, if you have a chiral molecule and if you polarize it, meaning if you charge polarize it, if you pull charge from one end of the molecule to the other, the motion of the electrons inside this chiral potential is spin selective. So essentially, every charge polarization in a chiral medium is accompanied by a spin polarization. And that spin polarization is chirality dependent, meaning if the up spin is moving more efficiently through a left-handed molecule, then down spin will move more efficiently in a right-handed one. So that is the cis effect. So how do we use this? Well, we need to essentially have a bias in electron spin, right? Because if chirality couples to electron spin, and if you have a bias in electron spin, then essentially you can use this bias in electron spin to have a bias in chirality. And that's what we want. We want an agent that strongly couples to chirality and biases it in one direction. So where do you get a bias in electron spin? Well, magnetic minerals, magnetized surfaces, have that bias in spin. Because like magnetization by definition is the net spin polarization. So this is the experiment that we did. Essentially, consider a magnetic surface and a surface process, like adsorption or crystallization on this magnetic surface. So the surface is magnetized, meaning it has more one spin state than the other. And molecules are approaching the surface. And they're in equal amounts. They're 50% L molecules and 50% D molecules. And as the molecules approach surfaces, or as the molecules approach themselves, there are like van der Waals forces between them. And there are dispersive forces between them, which leads to a transient charge polarization, as you see in the partial charges. And that charge polarization is agnostic to chirality. It happens the same way for left-handed and right-handed molecules. But what is not identical for left and right is the spin polarization. Because the charge polarization happening inside the chiral medium is spin selective, and that spin selectivity is chirality dependent. So if you have the down spin state for right-handed molecule, the red one, you will have the up spin state for the left-handed one. And because these spins start to interact with the surface spins, that's the moment where you break the symmetry. So now you realize singlet-like interactions, downspin, upspin interactions with the right-handed molecule, and you realize upspin, upspin interactions, triplet-like interactions with the left-handed molecule. And one is more energetically preferable than the other. So essentially you can think of it as the molecules come near the surface, they become magnetic, and the surface pushes one and pulls the other. So essentially promotes the crystallization of one and prevents the other's crystallization. And because this is a spin effect, not a magnetic effect, this is not a Zeeman effect, it is really strong. And it's on order of like 1 eV at room temperature. So you can realize this in dirty conditions that pertains to origin of life. So essentially magnetized surfaces break the chiral symmetry. So how did we realize this in a real scenario? Because it has to be also related to origin of life's chemistry, right? So we focused on a reaction that is really seminal to the synthesis of nucleotides, ribonucleotides. And I won't go into the details, but essentially there is a chemistry which can make the precursors of RNA in a very efficient way. And that chemistry has a molecule named RAO, which you see in the red boxes, which has very special properties. And this molecule is crystallizing at its very low concentration, and it has some preferable crystallization properties that can be coupled with our mechanism. So what we did is we essentially, and also this molecule is a direct precursor of RNA precursors like cytidine, uridine, the pyrimidine ribonucleotides. So essentially, if you can make this molecule homochiral, the chirality of this molecule directly determines the chirality of RNA. So it is the right precursor to work with. So what we did is we took this molecule in its racemic solution. So essentially, there was symmetry, right? The molecule had an equal presence in L and D, and then we crystallized this molecule on a magnetized surface. And in this experiment, the achiral magnetized surface, which is an oxide of iron named magnetite, essentially acted as a chiral reagent. The achiral magnetized surface acts like a chiral agent because of the spin effect that I described. And when we did this experiment, we realized that you get highly enantiomer-enriched crystals whose enantioselectivity depends on the magnetization state of the surface. So on the left, you see crystals on the magnetized surface, and on the right, you see CD spectra, circular dichroism spectra, which shows that you get L or D molecule dependent on the magnetization state of the surface. And we can actually repeat this and reach the homochirality in 2 crystallization steps. And with that, I would like to first thank my advisor, who is holding a rock that contains some of these magnetic minerals that came from Western Australia. And there's a lot of work, I did with collaborators in Israel, in the UK, and with that I end my talk. Obviously, this is not the whole story, so if you would like to know more, please read the papers, and don't hesitate to talk to me. Yeah.
Thanks for kind of beautiful work. Just a conceptual, logical question. No magnetic field is equivalent to taking two magnets opposite to each other and sort of mixing those.
Yeah.
So that means that one has the opposite effect of the other. So on Earth, obviously, you can have magnetic field reversals among the rocks on the surface of Earth, and also the magnetic field of the Earth is changing over time, right? It changed polarity. Changes. So my question is, why would one be favored over the other if there is this intrinsic symmetry that the average probability is the same for both magnetic directions?
Yeah, very good question. So we considered that. So for the magnetic reversals, there is some periodicity, right? Like probably unknown for Hadean Earth, but 100,000 years, something like that. But within that time frame, the minerals that are forming on one hemisphere is polarized in one direction. So there is like a hemisphere scale uniformity. And in that time frame, if you kickstart the prebiotic chemistry, essentially like what you realize is actually the kind of a feedback effect as well with the chiral molecules and the surface, which I didn't talk about. So I will quickly tell you about that. So in this state, let's say you start with a polarized surface that comes from the field of Earth, right? And then the molecules start crystallizing in an enantioselective way. And now you realize an excess in the chirality of molecules, right? So after that happens, the same effect can be translated from the chiral molecules to the surface as well. Meaning, just as the surface can select the chirality, the chiral molecules can magnetize the surface as well. And essentially, we did this experiment, and when in the presence of chiral molecules on the surface, if you flip the magnetic field, the surface magnetization doesn't flip, because the spin effect of the crystals protect the magnetization of the surface. So it is kind of a mutually reinforcing relationship between the chirality and the magnetization.
Okay, but can you explain why life chose this particular and not the other?
Oh, so is there? Okay, so that is a hard question, because we don't know exact history of the magnetic field of Earth, and we don't know at which time frame the prebiotic chemistry took place. Yeah, but essentially, in a local environment, you need to have a uniformity, and this scenario gives that. Yeah.
Please.
Related to this, can you hence infer something about the time scale on which life has formed? Because it must be related to how long can a magnetic field stay coherent.
Well, okay, so that is not a problem. That's what I'm saying. Once you started at a state that is uniform, after that, Earth's magnetic field can change, and everything can happen, but the magnetization state won't change.
Yeah. Okay.
Yeah. So essentially, you only need to kickstart it once with Earth's field. After that, Earth's field does not play a role.
So if we go to Mars and find life on Mars, you would expect chirality to be opposite potentially.
You cannot predict that.
Yes, so it will not be, but if we find that it's the same as Earth, then the two planets must have been connected somehow.
Maybe, or it's 1/2, right? Maybe.
No, right, but
maybe. I think asteroids actually will say a lot about that, because like you need more statistics, right? Like amino acids are left-handed, sugars are right-handed. Okay, so if we go to Mars and if it is the same way, maybe it's just chance. Maybe it is necessity. So we need to just find more numbers.
And also on Earth, one side of the Earth has an
Correct.
opposite polarity to the other
Correct.
side of the Earth. So I don't know if life was different in the two hemispheres of Earth.
But life probably started at one location, because we know that it can be traced back to Luca, right? Like there is one organism from which everything just came. Like life could have started in multiple locations at the same time, but the life we know it came from one location. The others could have died or could have not existed. Yeah.
Yes.
Where is that location relative to the magnetic field?
Right here.
I don't know.
You mean in Cambridge? No, because suppose we go to Australia and find the opposite polarity
Yeah.
for early life, that would be consistent with your picture, but you're saying just one dominated everywhere.
Yeah, I mean, because like, if life could have started in two different locations and both evolved, then we would have known that, right? Like, there's one Luca, and all life we know it right now came from that organism. And before Luca, perhaps there were other like common ancestors, but in their evolutionary history, they just died, and they could have been left-handed or right-handed. But the one that survived is one, and that happened at a location that I don't know.
Any other questions, comments? Please go ahead.
So I've wondered for a long time, so you have a physical chemical mechanism for the symmetry breaking.
Yeah.
Why isn't just spontaneous symmetry breaking enough? That is to say, why is it, like if you didn't have a magnetic field at all, then...
Because it's not persistent. Like in a prebiotic chemistry, you don't only make things once.
Well, but I mean, by chance you make ever so slightly more of one than the other, and then you have application, right? It's same as if you cool a metal down below the Curie temperature, it forms a magnetic field, and there's no reason for it to be one direction or the other, but one of them wins.
I mean,
right?
sure, but like first of all, like that has to be shown. I don't know any experiment that shows that it works that way. And second, let's say you did that, okay? You make like right-handed like nucleotides, and then you keep making things, right? You need to produce materials for a certain amount of time before biology can start off. And then the ones that come after doesn't necessarily, go the same way because it's a spontaneous symmetry breaking. If you deterministically push this things in the same direction and kept it persistently, only you can guarantee that it will go in one direction.
Well, it happens in metals, right? There are big regions that choose one polarity. So
there is only one reaction in chemistry that is known to produce spontaneous symmetry breaking. That's called Sohei reaction, and that is highly non-prebiotic. You cannot do it underwater. You need highly unrealistic conditions, and there is no prebiotic example of what you said.
Well, in particle physics, spontaneous symmetry breaking is a fundamental
Sure.
concept. And then what happens is sometimes there are domain walls separating two phases, and one is winning. So
Sure, I mean, I'm not against that. I just there is no example of that.
Okay, well, let's thank Furkan again for
Can you hear me?
Yes. Yes.
All right, so today I'll be talking about this exciting, pretty recent supernova that happened in M101. And then, this is the closest and brightest supernova in the last decade. So there's so much that we can do. And then I think we could observe this for coming 3 to 4 years. So this is a really exciting event. But I just want to introduce, Rachel already introduced supernovae, but I just want to focus on one specific type of supernovae, which is called hydrogen-rich supernova. So it's which we call type 2 supernova with hydrogen. And then what these are like core collapse explosion of red supergiants. So this is a stellar evolution in a nutshell, but what we are talking today is really this mass range of above 9 or 10 solar masses. They become red supergiant, forming iron core, and then the end result is the iron core collapse supernovae, leaving either neutron stars or black holes. And then jumping onto this particular supernova called 2023 IXF, that happened in M101, which is only 7 megaparsec away. So this is our neighbor. And as I said, this is the closest and brightest supernova in the last decade. And then what's even more amazing is that this was discovered by an amateur astronomer, like legendary amateur astronomer in Japan, who has his own network of telescopes at 3 different locations in Japan. So, and then as you can see, like, he has a bunch of monitors here, right? So each one corresponds to his telescope. So that really tells you like how many telescopes he has. Yeah. And then there is a dedicated article about this discovery in Science. So this is a news article in Science. So I highly encourage you guys to check this out. And then, yeah, so this was discovered by Koichi Itagaki in the really famous phase-on spiral, which is the M101. And then, so the fun story is that I was drinking at a bar on Friday evening, and then for some reason I checked emails, and then I realized his email saying like, you have to observe this. So, and another thing is that for some reason, again, I had my laptop with me. So I just opened up my laptop and then trigger, all the ground-based and space telescope that I had access to. So this is a fun story. And then, so this is image from, one of his observatory. And then you don't see, sorry, my hands are shaking. So you don't see anything at the red circle, which is the location of supernova. So, but 2 days later, he found this. So this is a new source. And then this turned out to be the supernova. And then if you make a color composite, this locates in a really, beautiful spiral arm on this M101. So pretty much all the professional astronomers started to follow this out. And then since this is a beautiful spiral, this is also really popular target for amateur astronomers. So after the fact that Itagaki discovered this supernova, amateur astronomers, looked at the images, and then some of them found the supernova in it, and then the others didn't find any. But given this, really the early rise phase of this, light curve, we could constrain the explosion epoch better within 2 hours. So this is really amazing. This usually doesn't happen. And then this is, again, a beautiful spiral in the nearby universe. So, professional astronomers had taken this, galaxy with, Hubble Space Telescope, Gemini, and Spitzer Telescope in this case. And then we could locate the location, we could, cross-correlate the supernova location to whatever source we see in the pre-explosion images. And then in this case, we could, point the progenitor. So this is called direct progenitor identification. And then this way, you can actually study the properties of the progenitor, which is really rare. And then it has to be in the nearby universe. And then you have to be lucky that there exist these archival images. And then if you construct an SED from these pre-explosion images, this is what you get. So the red points at a supernova SED, and then this light purple SED is a typical red supergiant that is without any dust surrounding it. And then, but the observed SED differs quite a bit from the red supergiant. So you need 2 components to actually construct this SED. This is the red supergiant component, and then this is the dust component. So from this, it was a really red supergiant with a mass loss rate of 10 to minus 4 solar masses per year or so. So this is kind of what you'd expect from standard theory of stellar evolution, 10 to minus 4 to 10 to minus 5 solar masses. What's even more interesting is that there are so many epochs of these archival images. So you could make a light curve of this progenitor, to see how the progenitor was behaving before the explosion. And then this is really interesting that you see this quasi-periodic light curve with a period roughly about 1,000 days. And then these amplitudes are huge. So here, these really small gray points are showing the light curve of Betelgeuse. So the amplitude is so much higher than what we observed in the Betelgeuse. So the star was doing something really interesting just before the explosion. And then, so coming to the supernova observations, I'm showing here the multi-band light curve. So you see the photometry from UV to near infrared, and then it peaked around 11th magnitude in apparent magnitude. So this was observable with a few centimeter telescope. So if you had any a telescope in your backyard, you could have observed this. So this is really unique. And then if you see the light curve, since it was discovered only 2 hours after the explosion, we could see the rise in 8 magnitude. So that's again so we see the rise about 2,000 times from the discovery to the peak. So, and then that was only happening in 5 days. So this is a really rapid rise. And then what's more interesting is that if you take the color light curve, in this case I'm showing U minus V band, and then you see this blue-white evolution in the RE phase. So if you think of a supernova like a typical supernova, you first see the so-called shock breakout, and then it cools down as it expands. So you'd only expect to see red-white evolution after the explosion, but in this case we saw blue-white. So there has to be something surrounding the progenitor, and then most likely the supernova ejecta is interacting with this so-called circumstellar medium. And then that's the only way you could see this blue-white evolution. And then if you look at the spectrum, so this is the spectral series. And then so this is from 1 day to 6.5 days after explosion. And then this almost futureless spectrum is what you'd expect to see if the progenitor is just a bare progenitor, not surrounded by any CSM. And then, so the fact that we see these, really complex narrow lines tells you there's something. And then this is caused by the supernova, supernova photons ionizing the surrounding medium. And then that way we see these, these emission lines from the circumstellar medium. And then what's interesting here is that like what we saw in the blue-white evolution, we saw transition. So I'm just showing C3 and C4. So in the first spectrum, so it's kind of hard to see, but they have roughly same strengths. But then as the time goes, C3 kind of disappeared, and then C4 got stronger. So this is telling something similar to what we saw in the U minus V color evolution, that the temperature at the photosphere is increasing. So this is, again, really interesting, shifts in the high, ionization state of this circumstellar medium. So I just want to put a picture here. So from these observations, I think what we saw is this red supergiant progenitor embedded in this really dense circumstellar material. And then explosion happened, and then we are seeing this supernova shock propagation inside the dense CSM. And then after a few days, this shock front broke out from this dense circumstellar medium, and then it transitioned to more or less normal supernova. So this is the just some illustrations. And then so given this fact, we try to model the light curve numerically, and then this is showing the light curve evolution as a function of time, and then the points are the data, and then it's color coded by the explosion energy. So in this case, I'm not putting any CSM. And then as you can see, these light curves, even if you increase the exposure time of explosion energy of 2 times 10 to 51 Earths, which is typically assumed to be the upper limit on the typical core collapse supernovae, you cannot reproduce the light curve peak. So there has to be some kind of another power source that's powering around the light curve. So in this case, since we saw the evidence of CSM from the observations, I put CSM with a typical red supergiant might have mass loss rate of up to 10 to minus 4 solar masses or so. And then that's shown here with the purple light curve. So again, that has no significant effect on enhancing this luminosity around the peak. But if you add this yellowish light curve showing extreme mass loss rate of 1 solar masses per year or so, and then So that's what's really required to reproduce this light curve. So this really tells there is a really period of enhanced mass loss, maybe a year or two before the explosion. So this is like really crazy. You lose a mass of sun in a year. So if you think about it, this is insane. But one problem with that is like if you focus on the early phase, so these are the amateur detections, and then the best fit that I mentioned in the previous plot is this 1 solar mass per year of mass loss. But this really overshoots these amateur measurements, so it has to go down like this. So there might be a decreasing like in mass loss, roughly like 0.7 to 0.4 years before explosion. So here we are seeing really variable like mass loss rates in the a year or two before explosion. So this is really interesting. This really tells us there is a complex CSM from really variable mass loss right before explosion. So coming back to this picture, and this is my summary slide. So we know like from the progenitor detection, the underlying mass loss rate is 10 to minus 4 solar masses per year or so. But then there is this dense, more like a shell of CSM, which extends to 3 to 7 times 10 to 40 centimeters. And then the CSM mass inside that shell is about 0.1 to 0.7 solar masses that's moving at 100 kilometers or so. So this is what we got from the observations. And then this is showing like, supernova explosion happened, and then that's about 10,000 kilometers per second. That's how fast this supernova ejector is moving, and then that is what's interacting with this really dense CSM. And then there's independent X-ray measurements at later time, like 5 days after the explosion, after the shock, passes through this dense part. Then the estimates from there is about 10 to minus 4 solar masses per year. So from here, I think we are seeing this underlying really low density circumstellar medium. But there is no synchrotron radio emission. This is actually the work by Ito, his first author paper in the last decade. And the limit that you get is like, about a millijansky. So this is telling like probably during the phase where the shock was propagating this dense part, it was just too much like free absorption that we didn't see this radio emission. But once it was outside this thick shell, I guess the synchrotron radiation was just too weak to be detected. So I think this is a really consistent picture here of what we saw in this really exciting supernova. So that's it. Thanks for listening.
And I guess the most important lesson from what we heard is that you should always take your laptop to a restaurant.
Yeah, I'm not saying to the students, but...
But the question I had is 7 megaparsecs. Could the supercommunicanda detect a single neutrino from there?
So I think people looked at it, but the answer was no. So it was not, yeah. I think I think Super K now goes up to 1 megaparsec or so. So it was just a bit too distant.
Okay, but in principle, if there were jets, we could have gotten more than the standard supernova yield. But they checked and they didn't see anything.
Yes.
Okay.
So I guess, yeah, that's a good point. So I think we can I think we're confident that there was no strong jet that broke out the the circumstellar medium.
Yes. Igor.
Why are you calling it the nearest supernova? I think that the one in M82, which was SN1A, it's more nearby.
So sorry.
So it's
what I
close core collapse.
Yeah. So what I meant is the closest and brightest from the Earth. Yeah.
Any other? Dimitar?
This model is assuming a spherically symmetric mass loss.
Right. Yeah.
What will happen if it's not?
So yeah, that's a really good question. So one way to one way that you can actually change this picture is like, what if the circumstellar medium is has some asymmetry, maybe a binary interaction or something? Then depending on your line of sight, you might see optical from the disk region, and then reprocessed X-ray or radio from less dense region. So that's another way to explain this. But our numerical model just simply assumes precursor symmetry.
Evan?
Sort of similar question. I noticed when you were first modeling the CSM, you sort of have a m.dot wind term, and I get why you might do that in terms of 1D modeling, but it's really, the picture I should have is not a wind, right? It's more like an eruption or something that seems to happen.
It's probably radiation pressure and it's pushing a lot of the envelope.
Yeah.
It sounds like a huge pulse of like one solar mass of material in the last year or a few months or something, right?
Yeah.
And it maybe could be clumpy or have a complicated geometry.
Yeah, thanks for asking that question. So we actually did the modeling, but I just didn't have time to show here. But the picture that you get is really similar. So you have to have this kind of like, let's say 0.5 solar mass of ejection in the last year or so, and then that is like, accelerated by radiation pressure, and then you could get a really like similar conclusion that we got from just assuming a constant wind case.
Morgan, did you want to add a
Well,
comment?
I was curious, when in that pulsation that you saw beforehand, did it explode? And like when is, a half year beforehand when you think this shell?
Yeah, so that's
phase?
that's another good question. So from the periodic light gap you saw in the projector, that only goes up to 3 years before the explosion. So
But what if you take that period and go forward?
I think it's going to get close to the maximum.
Yeah, interesting.
Yeah,
That is
but
when it explodes?
yeah.
Uh-huh.
So this was discovered in May of this year, and then I think if you just extrapolate that periodicity, then you'd get the peak around there.
If it was like a shell coming off at minimum, that would be when it's most expanded. So that would kind of like...
Yeah, but there are there exist a few data points like soon before the explosion, but those are kind of contradicting each other. Like one filter is increasing, the other filter is decreasing. So
super interesting.
We went beyond our time limit as a testimony to how exciting this is. We are already 15 minutes beyond, so we have to conclude here, and any other questions can be directed.
yeah, thank you so much.
Thank you.
What's the time scale for this?
I was like, this is journal club paying off for 7 years.
Every week?
Yes.
Like right away? Well, so in other words, before our big proposal is due in November.